Okay. Now, Newton-Raphson method, again, it is the standard method to solve nonlinear equations. This is the most appealing method because of it is a very fast convergence rate. And today we'll demonstrate this. And we will compare it to the previous one. Just before I move forward, I checked the quiz, the challenging quiz, and I found 3 answers. I think 2 of them are correct, which is very good, and 2 they are different. But for those who tried the quiz, you would see that it's challenging to come up with a function that is converging. And for some other functions, it's even more and more challenging. So this is why it's very dealing with single point iteration or the Gauss-Seidel is not very straightforward, especially when you deal with nonlinear equations. And this is a reason why Newton-Raphson is preferable, because it's very straightforward. It has its flaws, nothing is perfect, but when you compare it to the Gauss-Seidel, it is way better than the Gauss-Seidel method. Okay, so let's start. So it is as I just mentioned, it's the most accepted, widely used method to solve simultaneous nonlinear equations. And it is, as we know it from when we find the roots for a single equation, basically it is x of I plus 1, which is the current iteration, equal to x of I, which is the previous value of the iteration, or the initial guess could be, minus f of x divided by f prime of x. So this is how we set our Newton-Raphson. Now, this is for one variable only. Now, we will have n number of equations. So we'll have an n number of variables. So x now will not be a number. Instead, it will be a vector. And xi will be also a vector. And here, f prime of x will not be a number, but it will be a matrix. And it will be an inverse of a matrix. So without any proof, intuitively we can say that in the format of Newton-Raphson, when we have multiple equations, that's how it will look like. This is a vector, so this is like x1, x2, xn at k plus 1. And x of k is the same thing, but at xk, which is the current or the previous iteration. Now, this is what we need to understand how to deal with. Now, this is your f of x. F of x will be a vector here, okay? But f prime of x inverse, now this will be a matrix. And this matrix, we call it the Jacobian matrix. And let's look carefully to this. If you look here to the first line, it's the partial derivative of f of 1, which is the first function, with respect to the first variable. The second item is the partial derivative of f of 1 with respect to the second variable, and so on and so forth. Then when we go to the second line, we go for the second function, and we do exactly the same thing. If this symbol is not familiar to you, it's not a big difference between this and this. It's almost the same. The only difference between this and this is the derivative, this is the partial derivative. So what does it mean? It means that if my equation has more than one variable, then I use this symbol. So this is the partial derivative with respect to x. Then I could have the partial derivative with respect to y, because I have x and y. So I cannot use this when we have more than one variable in the equation. I'm not sure if you have seen this before or not, but this is in a nutshell. It's very straightforward, nothing new here. Okay. Now, so this is how we can derive the Newton-Raphson method using our previous knowledge. However, I will take another approach to prove to you first this, and then we go for the set of equations. We used, if you remember, to derive this, the graph. Okay, a question here says, what if one? Okay, here I'm having multiple equations. I mean, like for example, f1 could be, for example, x squared minus 2xy plus z equal to 0. This is f1. f2 is equal to 2x minus root of y plus z squared equal to 10. And f3 equal to 4x plus xy equal to 15. So these are three equations with three variables, x, y, and z. So this is your f1, this is f2, and this is f3. So now here I need to find the partial derivative of f1 with respect to x, the partial derivative of 1 with respect to y, and the partial derivative of 1 with respect to z. And then I move here to the partial derivative of f2 with respect to x, and so on and so forth. Okay, so this is what is meant f1 and f2. And we'll have examples to demonstrate this. Now, consider that I have, let's go back to the one dimension. Now, I will prove to you whatever we had from the graph. If you remember, when we have the graph and we defined our derivative of f of x, then we came up with the formula from the graph, from the slope of the line. We said that now the current or the future iteration, how it is related to the previous one. But now I will use another approach, which is the Taylor expansion. Now, if this is my f of x equal to 0, it's a nonlinear equation, so it's just now one-dimensional. Let's go back to the one-dimensional. It's an interesting way of proving the Newton-Raphson formula. Okay. Now, assume that I start with an initial guess delta x of 0. So, x of 0. This is my initial guess. Now, my initial guess is usually deviated from the actual answer by delta x of 0. Meaning that, for example, if I start my initial guess by 5, but the actual answer is 6. So, between 5 and 6, there's a delta x, which is 1. So, this is the error. Okay? So, if I try to calculate f of x at 0, it will not equal to 0 because that's not the right answer. However, if I add to it the error or the deviation between your initial guess and the actual answer, then this will be true. Now, in this equation, what is the unknown? Is this delta x? And as a matter of fact, we are trying to estimate or to find delta x or the error. So the Newton-Raphson method, basically, we are trying to find the error, as we will see. Now, if we use the Taylor series expansion, this is equal to this: f of x at 0 plus the derivative of x with respect to x times delta x of 0. This 0 is all referred to the initial guess, plus 1/2 or 1/2 factorial, the second derivative of f with respect to delta x squared, second derivative, 0 delta x 0 plus, and we can move on. And so if I come and cancel all of these, any term higher than the first derivative, so from this you can say that your delta x of 0 will equal to what? Will equal to minus f of x of 0 divided by df by dx of 0. This is your error. Okay. Now, so your x of 1, which is the now the current guess, will be what? Will be the previous guess plus delta x of 0, which is this one. And this will lead us to the formula of the Newton-Raphson. So if this is your error, is equal to this. Actually, this is the error. So your x of 1, the current iteration, equal to the previous one plus delta x of 0, and this is what we used to say: x of I plus 1 equal to x of I minus f of x of I divided by f prime of x of I. So this is exactly the same formula, exactly the same one. Okay, so we can prove the Newton-Raphson from a graph, or we can prove it from the Taylor expansion, approximation to the Taylor expansion. Excellent. Okay, now let's move on now from going from, now we need to expand on this, and let's see how we can derive the Newton-Raphson formulation for a set of equations. Now, I don't have just one non-linear equation. I have a set of non-linear equations. Now, the number of variables, as you know, has to be equal to the number of equations. So I have an n-dimensional equations. So I have n number of equations, and I have an n number of variables, as you can see here. Okay. So now I'm trying to estimate the formulation for the Newton-Raphson. How to do that? Now I will expand. Now each one will have its own Taylor expansion. So what I will do, I will show you the Taylor expansion, but after the truncation of all higher order than the first derivative. Okay. So if we do that, these are the Taylor expansion. This is for the first equation, the second, and here is to the n equation. So if you look carefully here, what we have here, we have the function defined as the initial guess, which is 0. And then we have the partial derivative of f1 with respect to x1 times delta x1, plus the partial derivative of f1, the same function with respect to the second variable, which is x2, and so on and so forth until I reach the partial derivative of f1 with respect to x of n times delta x of n. So this is my first equation, second and third. So what I will do, I will move this one, not remove, move this one to here. So it becomes with a minus sign. Okay, and this vector will equal, I want to put this in a matrix form like this. Okay, if you multiply this row with this column, you get the first line. Okay, and I just moved this one here. Now when you look to this equation, what are my unknowns? Let's look. This vector, it is known. Why? Because this is the functions, the equations that I have defined at the initial guess. So I know the initial guess and I know the function. So these are numbers for me, actually. So these are all numbers. Excellent. What is this? Now this is taking the partial derivative of the function in the first row with respect to every single variable. So when I do that, then I substitute with my initial guess with this equation. Okay, so when I do that, I will have also numbers. So this will be a matrix filled with numbers. The last one is this is my error, delta x1, delta x2 until delta x of n. So this is what I want to find. And here, and once I know this, then I will update my value. Once I know the error, I will update my x1 of 1 is equal to x1 of 0 plus the delta x of 0. This is, I will get it from this equation, and this is my previous guess. I will update x2 as well. 1 is equal to x2 from the previous plus delta x of 0. Now how to solve this? If I take the inverse of this matrix and multiply by both sides, then I can find this. Or I can use Gauss elimination, or I can use any solver for linear equations. And this is the beauty of the Newton-Raphson. So basically what I have done, I changed a set of nonlinear equations into a set of linear equations. So I'm linearizing the system of the equations, and that become much easier to deal with. Okay, so this is the whole idea of the Newton-Raphson. So let's have some examples. Okay, so here this is the first example. This is my f of 1 is equal to this, and this is my f of 2 equal to this. And here this is the format. If you recall, in the Gauss-Seidel, I have to put it in a format that x is equal to g of x and y is equal to g1. This is g2 x of y. This is how I put it in that format. Okay, and this is what's tricky in this, because sometimes it converges, sometimes it doesn't converge. If you follow the condition we established in the last class, as the partial derivative of the function with respect to x1 absolute value plus the absolute value of the partial derivative with respect to y has to be less than 1, the summation of these two values. And this has to be applied for all functions. Okay, so That's not easy to deal with, but this is one is more straightforward. Okay, so this is my function now. Okay, so the vector f, or if this is the one that is I'm trying to, this is my vector. Okay, so this vector f is basically nothing but y plus x squared minus 0.5 minus x, and x squared minus 5xy minus y. Okay, so this is my f. Now, if I want to find my f at 0, my initial guess, which is this one. Okay, so I want to find f at 0. Okay, so I will substitute here the values. F of 0. What is f of 0? So I'll substitute x equal to 1 and y equal to 0. So this is 0 plus 1 minus 0.5 minus x. So this is minus 0.5. And then do the same thing here. And this is equal to 1. Okay. So this is my f of 0. What is my f of 0? Is this vector. Now, let me see the Jacobian matrix. Now, what the Jacobian matrix, or what we call it here f prime, this will be the f1 with respect to x, f1 with respect to y, and then f of 2 with respect to x, and f of 2 with respect to y. So this is my Jacobian matrix. Let me see if there's any question. No, nothing. Okay, excellent. Okay, so now let's calculate this. Let's do this. Solve this exercise until the end, step by step. Okay, so let's go here. So I want to find the partial derivative of f of 1 with respect to x. And when you do this, since I'm taking the derivative with respect to x, this becomes a 0 because y now is a constant. This becomes 2x. This is 0. This is minus 1. So this becomes 2x minus 1. If I take the partial derivative of f of 1 with respect to y, this 0, this 0, this 0, and this becomes equal to 1. So this is the first row in my matrix, or the Jacobian matrix. Then I will move to the second row, the partial derivative of f of 2 with respect to x. So it will becomes equal to 2x. This is the first term. Here it becomes minus 5y, and the rest is 0. And finally, the partial derivative of f of 2 with respect to y. Again, this is 0. This becomes minus 5x, and then minus 1. Okay, now this is in symbolic way. Then I have to calculate this f of prime, but at 0. What is this? This is nothing but this matrix. Okay, excellent. So we'll do this. Now, if I substitute the values to x minus 1, okay, so this becomes equal to 1, 1, 2, and minus 6. Just substitute x and y with this value. I am set now. I found f of 0. I found f prime of 0. Then I can find the error. Okay, so now I can find my error, delta of x, delta of y will equal to minus the Jacobian 1, okay, 1, 2 minus 6 inverse times minus 0.5 and 1. From where I get this? Because originally this was like this. You will have the following: minus 0.5 and 1 equal to the Jacobian matrix, which is 1, 1, 2 minus 6 times delta x and delta y. So this is how it looks like. Okay, well, from where I get this, this is exactly this equation. Okay, so now I need to move this to the other side. So I multiply by the inverse of the Jacobian matrix, and this is what I did. I just multiply both sides by this inverse, and I get delta x. Now, if I add to this, you can find x and y for the first, this is equal to x and y 0 minus all of this. 1, 1, 2, minus 6, inverse, minus 0.5 and 1. And now substitute. What was x and y? It was 1 and 0. This is my initial guess, times 1, 1, 2, minus 6, minus 0.5 and 1. Remember, all of this is nothing but delta x, delta y. That's it. So I'm adding my reference to the error that I'm calculating. So this, all of this with the minus is the error. So I'm adding it now. So if you do this, you will see this is equal to 1.25 and 0.25. So this becomes your x, and this is your y. So we started with 1, 0, and now 1.25 to 0.25. And then what we do, we go for the second iteration, and so on and so forth. If you do for the second iteration, you will find that your x and y are equal to this. Okay. Okay, sorry. I was muted. Okay, I'm really sorry about that. Okay, let me just go back and say what I just said. The inverse of a 2 by 2 matrix is very straightforward. Okay, all you need to find is to find the I'm quite sure you covered that in linear courses, linear algebra courses. What you need is to find the determinant, and then the inverse becomes one over the determinant, and then you switch these two variables and you change the sign of these two. So if you just go and look into your notes how to find a 2 by 2 matrix inverse, it's very, very straightforward. The question is not how to find the 2 by 2 matrix inverse, is how to find a 3 by 3, 4 by 4. This is a challenging one. 2 by 2 is straightforward. You can easily do it. We will see how we will handle higher order equations. But now I want to demonstrate another thing here. This equation we did before in Gauss-Seidel method. And we have seen that this took us a very high number of iterations, I think 15 iterations, to reach to the required accuracy. Now, the reason I'm asking, I want to solve this, I want to see how this Newton-Raphson method is different in terms of the conversion rate. Now, this equation has been set to be suitable to work with the Gauss-Seidel, x equal to y equal to, but this is not the format we want. So here we have to change the format to f of 1 equal to, I move this to the other side, is equal to 0.7 sine of x plus 0.2 cosine of y minus x. So this is your f1, and your f2 equal to 0.7 cosine x minus 0.2 sine y minus y. So now the equation is set in the right format. This is equal to 0, and this is equal to 0. Okay. So let's find now. The initial guess will be 0, 0. So this is my initial guess. So my iteration, which is x1, y1, will equal to this 0 minus the Jacobian matrix inverse times f of 1, f of 2. So this is how we set. Now, if this is 3 by 3 variables, becomes, we add a 0, this becomes 3 by, this is 2 by 2 now. If it is 3, it becomes 3 by 3, and this is 2 by 1. So we have 2 by 1, 2 by 1, 2 by 1 system. Okay. Now, let's find the Jacobian. Now, what the Jacobian will be? The Jacobian matrix will be the partial derivative of f1 with respect to x, the partial derivative of f1 with respect to y, the partial derivative of f2, with respect f2 with respect to x, the partial derivative of f2 with respect to y. Okay. So from this, what is the partial derivative of f1 with respect to x? This is equal to 0.7 cosine x. This goes to 0. This becomes minus 1. Now, if I substitute 0 and 0, so this is become as my initial guess. So this becomes equal to 0.7 minus 1, which is minus 0.3. So I found this first element. Now let me do partial derivative of f1 with respect to y. So I will do the same thing. So this becomes minus 0.2 cosine y. The rest equal to 0, which is equal to 0. Now I have a question here. You said that f1 and 2 are equal to 0. However, wouldn't we have to sub in our initial guess for x and y to determine what the initial value of f1 and we don't know the initial f1 and f of 2 is an equation equal to 0. F of x, y is equal to 0. So this is the equation. But the x and the y, this is the initial guess. So we don't have an initial guess of f1 and f of 2, but we have an initial guess of the variables. And here it's given to us. And always it will be given to us. The variables will be given to us. Okay. Now let's find partial derivative of f of 1, f of 2 with respect to x. And this is, if you take this, should be minus 2 and not f of 1. Oh, I see your point. Yes, you're right. Okay, I think this is a typo here. Okay, I think even in the notes here. So this is, we need to take the partial derivative of f of 1 with respect to y. So this will be equal. Sorry, this is not. This is actually, when you take it with respect to y, it is minus 0.2 sine of x, sine of y. Sorry. Okay, so it is equal to 0 actually. Okay, but thank you for this. This is, I think this is a table even in the notes. So when we take the partial derivative of this one with respect to y, this goes to 0, this goes to 0, and this becomes minus 0.2 sine of y. When you substitute, this becomes equal to 0. Okay, hopefully this is clarified. Now we'll do the same thing, partial derivative of f of 2, which is this one with respect to x. So respect to s, so this goes to 0, this goes to 0. So the only thing you have here is minus 0.7 sine of x. Then this is equal to 0 as well. And then finally, partial derivative of f of 2 with respect to y. This becomes equal to 0, and this becomes minus 0.2 cosine function. So here with respect to y, so this is becomes this was sine, so this becomes cosine y minus 1, okay, and this is equal to minus 1.2. So there's a couple of typos. I will take care of them and I will fix them. Okay. So now this is what. So I found this, and here f1 and f2 easily I can substitute in the function. Remember, f1 is equal to 0.7 sine of x plus 0.2 cosine of y minus x. So now I'll substitute everything was equal to 0. Okay, so substitute x. This is goes to 0. This becomes 0.2. Okay, and f of 2. Again, this is add 0. F of 2 add 0 is equal to, as we know that f of 2 is equal to 0.7 cosine x minus 0.2 sine y minus y is equal, of course, is equal to 0.7 because everything here else goes to 0. So I know this one. I know this vector. So now I can find my value of x1 and x2 is equal to this. Now, if I do couple of iterations, you will find that I reach to the answer after only 4 iterations. I will reach to very less than 0.1%. If you recall, the criteria was both answers has to be less than 0.1%. So there I needed 15 iterations to reach to this. Here I needed only 4 iterations, which demonstrate to you how good is the Newton-Raphson. Okay. The last example I'd like to go with you, which is an interesting example, and you will have in the practice problem a similar question like this, which when you have a 3x3 system. Now, when it comes to 3x3 systems or 4x4 system, finding the inverse of the matrix by hand calculation is not a straightforward job. It's a very lengthy job. So what should we do? Okay, we need to solve the system of equations. We have linear set of equations. So what we do, we just apply Gauss elimination, as simple as that. So that's what should we do. Okay, so here we have now this. We have 3 equations. So this is your f of 1, this is your f of 2, and this is your f of 3. It doesn't matter how ugly it looks like, very complicated functions. It doesn't really matter. The Newton-Raphson can deal with any degree of nonlinearity. And these are my initial guess. Okay. And we need to apply 5 iterations. Of course, in the exam, I won't ask you to do 5 iterations. Maximum 2 iterations. That is the maximum of number of iterations that I might ask you to do. Okay, so this will lead to a system of equations. Now I need to put everything in that format. So I need to have x of 1. Now here x1, x2, and x3. So this, my vector becomes equal to this, x1, x2, x3. And this is after first iteration equal to x1, x2, x3. And this is my 0 iteration minus the Jacobian matrix times my f1, f2, f3 at the 0 iteration. And this is also at the 0 iteration. So I need to find the Jacobian matrix. And I need to find f1, f2, and 3. And f3 with the substitution of these variables. Once I am done, and this is already, this vector is this vector. Once I know the Jacobian, once I know f1, f2, and f3, then I can find my initial guess. Okay, so very straightforward here. This is not difficult. So you have your f of x, the 3 functions, and I just substitute the values. So what I do here, let me just go back here. So I will substitute x1.1. So this becomes 3 times 0.1 minus cosine. This becomes 0.1 times minus 0.1 minus 1/2. And you have to make sure that these are in radians. When you have an x that has numbers and angles, so this has to be a radian. It cannot be in degrees. Okay, minus 1/2. And you find your answer. So if you do that, you will find that your f of 1 is equal to minus 1.1 1995. Now it depends how many significant digits you can use. If I specify, then you use whatever I specified. If I not, then you use a reasonable number, like 3, 4 significant digits. That should be fine. And this is equal to minus 2.2698, etc. And this is equal to 8.4620. So this is your f of x. Now I need to find the Jacobian matrix. Now what will be the Jacobian matrix? Will be the partial derivative of f with respect to x1, partial derivative of f1, of course, f of 1 with respect to x2, and the partial derivative of f1 with respect to x3. Then the partial derivative of f of 2 with respect to x1, partial derivative of f of 2 with respect to x2, and the partial derivative of f of 2 with respect to x3. Finally, partial derivative of f of 3 with respect to x of 1, partial derivative of f of 3 with respect to x2, and partial derivative of f of 3 with respect to x3. Okay? So this is the matrix, and then I will use the initial guess to find the values, because this has to be numbers. Okay? It starts with symbolic by taking the partial derivative, and then you will convert that into numbers. Okay? So if we take only the first function, f of 1, that will do just the first one, and then you can follow the rest. So f of 1 that we have in our is equal to 3x1 minus cosine of x2 x3 minus half. So this is your f of 1. So I take f of 1 with respect to x of 1, which is this item. This is equal to 3. This is equal to 0. Partial derivative of f of 1 with respect to x of 2. Okay. So the derivative of this becomes minus x of 3 sine of x2 x3. So this becomes equal to positive sine x3 times sine of x2 and x3. Finally, the partial derivative of f of 1 with respect to x3. So now again this goes to 0, this goes to 0, so this becomes minus x of 2 sine of x2 x3. Okay, and then I will come and substitute the values. Okay, so if I substitute the values, this is 3, this is equal to 0.000999 something, and this is equal to minus 0.0094 or 999, etc. Okay, so this is the values. I finish the first line, I go for the second line, and for the third line. Okay, excellent. So let me move on here. So this is what we have. Now, what do we have here? Now remember, it is the Jacobian times the variables, the deltas that we have, delta of the error, delta x1, delta x2, delta x of 3, equal to minus f1, f2, f3. So this is how it's set up. Then we multiply by the inverse. Okay. Now I will not multiply by the inverse because this is a 3 by 3 matrix. So what we will do here, so let me write down here the values that I have. 3.00099 minus 0.00099, 0.2 minus 32.4. I'm just calculating the second line. I did not do that now, but I just take the values. You can verify this yourself. And then we'll have minus 0.099 minus 0.9920. Okay, excellent. So this is my Jacobian matrix. This is my variables, delta x1, delta x2, delta x3, that I will do, and this is equal to minus f1, f2, and f3, and if substitute, this is equal to minus, so this is equal to minus 1.199, minus 2.2698, and 8.462. Okay, so this is our system of equations. Now, for 2 by 2, I said you multiply by the inverse of this, both sides, you find the error. This is your error, that you want to go and add it to the original guess. Now, as I said, doing this 3 by 3 by hand is difficult. By 4 by 4 is very, very difficult. And in the exam or in the quiz, you are not allowed to use MATLAB. You have to show the steps. So how we solve this? This is something we are familiar with. We can use Gauss elimination. How to that? We use the augmented matrix. So I bought this is 3.00099 minus 0.00099, and then I add here minus 1.199. Move to second line, 0.2 minus 32.4, 0.995, and this is equal to plus 2.26098 minus 0.099 minus 0.09920, and then minus 8.462. Okay, now this becomes a Jacobian matrix. This becomes, we will use the Gaussian elimination, which is based on backward and forward substitution. Okay, so forward elimination and backward substitution. So we want to make this this is 0, 0, and this is 0, and then use the backward substitution. Exactly the same thing. Okay, so this is something I leave it for you to solve. This is exactly what we do. So this is very important here. I'd like to highlight this. When it comes to dealing with more than 2 by 2 systems of equations, then you have to use the Gauss elimination. So this topic that we covered in the previous set of notes, you will need it in this set of notes. Okay, so expect in the quiz a question like this, where you have a 3 by 3 or even 4 by 4 system. Then you have to use the Gaussian elimination. Now let me just go through the solution with you now. So this is the error that we found. Then we add the error to the, this is my initial guess. If you look, this is x0, and this is my error that I added. So this is my values, which is, this is my initial guess. This is my first values for x1, x2, and x3. Now, if I keep on doing this, you will find that the answer is converging to these